So, what exactly is a transformer? Well, yeah, it's trying to convert a one voltage into another. So you might have a primary voltage which is on the left hand side, and that's going to be turning into a secondary voltage which is on the right hand side. So let's use their color codes. We'll make that one blue, or let's make the arrow, I don't know, green. But when they do that, so the way they do that is by changing electric current into a magnetic field, and then turn the magnetic field into another electric current. And this combination of these different strengths of magnets changes the type of electricity, the type of voltage and current you get over the other side. Now, whenever you do and we'll look at how it does that in a moment. Whenever you do change the voltage, you will also change the current. And the reason for that is because the efficiency of a transformer is very, very high. So efficiency is around about 100%. So that means that the power in, or we could say the primary power, the power on the left-hand side, is about equal to the power on the right-hand side, the secondary power. So let's just give that the right colors as well. Okay. And oops, I want that to be blue, don't I? Yeah. So now we want an equation, use the right equation for power, and that is we know that so power, electrical power, is current times voltage. So basically, the current on the left hand side, the primary current multiplied by the primary voltage. So these are the current and the voltage on the left hand side. If we zoom in, you can see it's labeled IP and VP. That is going to be roughly equal to the power on the right hand side. So IP and not IP, IS times VS. Okay, does that make sense? So I've just instead of writing power, I've written what power is equal to. So when I rearrange this equation, so we can just imagine that's an equal sign. Remember, it's not exactly equal; it's nearly equal to it because the efficiency is nearly 100%. But we can just pretty much say that it is, because generally speaking, you assume that it is. So from now on, I'm just going to write a regular equals sign. So if I rearrange this, IP over IS, and we're just going to write equals instead of roughly equal to it, VS over VP. So I just rearrange that. So this means that the ratio of the current is the inverse of the ratio of the voltage. So when I increase the current, I'll decrease the voltage, or when I increase the voltage, I'll decrease the current. So that's the reason why whenever you step up the voltage, you're going to step down the current. But when they refer to a transformer as a step-up transformer, they're referring to the voltage. They're stepping up the voltage. So always think in terms of voltage. If you're trying to remember which one is which, when you're stepping up something, you're stepping up the voltage. But when you step up the voltage, you're going to step down the current because of this equation here. Okay? So the next thing you need to understand is why would you do it? And then we're going to look at how. So why would you step up the voltage? Well, when you step up the voltage, you step down the current, as I said a moment ago. And when you step down the current, it reduces the energy loss. Okay? So we can say lower current means less energy loss. Exactly. Well, and so this is like if you're transmitting energy over a long distance, if you're transporting electricity along power lines from where the power station is to where the houses are, then you're going to want to step up the voltage, because when you step up the voltage, you'll step down the current, and that means you'll lose less energy along the power lines. So power lines have a very, very high voltage because the voltage has been stepped up, and the voltage was stepped up so as the current could be stepped down. Okay, so they used it. So when you go from a power station to the power lines, then that's using a step-up transformer. Now, so why would you step it down again? What's the advantage of stepping it down? It's because it's safer. So lower current is less energy loss, but a high voltage is dangerous. Now, I'm not going to go into why at this point, but high voltage is dangerous. So if we have a high voltage in a sort of residential area, then there's more chance of electrocution, and so we step it down once we get to the houses. And so in residential areas, then you're going to the voltage is actually going to be 230. Well, in the UK, it's 230 volts in the UK. No, that's been decided. I mean, it's fairly dangerous, but there's a trade-off, right? I wouldn't stick a fork in a plug socket, but but it's 230 volts in the UK, and so that's what's deemed sort of safe enough to do that. I think in the US it's 240, and yeah, so I think that's right anyway. But the point is, you do need to know this number for some reason. Your exam board would like you to know that it's 230 volts. I'm not quite sure how that's going to help you in the future, but you will get the odd mark here and there if you know that number. So that's the explanation why you would step up, why you would step down, and also relating it to this equation here. And the next one is how you would step up or step down. And I guess I won't completely explain how, but I will tell you how to calculate it. So if you have a difference of the number of turns, in this case, you've got the number of turns here, which we can call NP, so the primary turns. It says winding here. It just means how many times it's gone around the coil, around the core, I should say, the transformer core. And then you've got the NS, so that's a secondary turn, so secondary winding. Again, how many times it's gone over that. So if it is that the secondary turns is greater than the primary turns, then this is going to produce a step up transformer. So that means it's going to the voltage will increase, which means that the current will decrease. Okay. So if it was the other way around, then you'd have it would produce the opposite effect. And if it was equal, then there wouldn't be any point to the transformer, because you're just having exactly the same current and the same voltage. So the next thing is to actually bring in the second sign equation, which is this one here. And if you have a look at this ratio, the ratio of the voltages is equal to the ratios of the turns. So if I were to double the number of turns, so let's say when from 500 turns on the primary coil, primary coil, and then 1,000 turns on the secondary coil, I'm going to also double the voltage. But when I double the voltage, I will then halve the current as well. Okay. So that's basically all you need to know about transformers, and then it's just applying it to these situations. So if we just look at this question here, let's just quickly do this question. In fact, so we did that one. So we're stepping up the transformer. No, sorry, we stepped down the voltage, so it's a step down transformer. And this one, it's giving you the primary coil has got 4,600. The secondary coil has got 300. So we're going to use this equation up here. This equation here to calculate the number of turns. Sorry, the voltage. Oh, I've written it down already. So the primary coil is 4,006. Oops, that's a bit thick, isn't it? Let's get that quite a lot thinner. So 4,600 divided by 300. So there's the primary, right? There's the secondary. So NP/NS, and that's going to be equal to the primary voltage divided by the secondary voltage. Now, the primary voltage we've already got. It's 230, which is, as I said, the UK power, UK voltage. We can flip this using that little trick, the algebraic trick I did a moment ago. So VS over VP is equal to, and we flip the right hand side to 300 over 4,600. And then we can multiply both sides by VP. So we can move that up here. And we can just delete that there. So VS is going to be 300 divided by 4,600 multiplied by VP, which is 230. Okay?